Hi everyone, this is a material balance group, Oletex Sdn Bhd, which is from group 14. We will introduce ourselves. Hi, I'm Niza bin Jaludi Rajagoba. My matrix number is 197337.
My name is Hisham Sadiq Kubait Katan. My matric number is 195005.
I'm Rubraj Yadavan 198240.
Hi, I'm Atira Vitasmi 199208.
This is our material balance project for SEM 1 1819 ECH3114 design project. So as you can see, this is our body flow diagram, which consists of 10 units, and each unit have its specific temperature and pressure, and its specific flow rates also, and its compositions based on our own calculation. And our raw material was methanol, and our feed rate is as 1000 ton per year. So in the process selection route, our process 10 units starts from input from a cracking reactor, followed by a splitter, which is split into two streams, top streams and bottom streams, where the top streams enters a condenser and mixed back to the bottom stream, which is in the mixer, and from the mixer is moved to the distillation reactor, reactive distillation reactor, and from the distillation reactor moves to splitter, where it splits to two streams, top and bottom. Top stream enters a quench and comes back to a mixer, and then, from the splitter itself directly goes another stream into a mixer and going into a separation column. In a separation column, the one of our output will coming out from a separation column, another output is coming up going to quench, and coming out from the coming out from quench. So you can see here, our feed is methanol at a basis of 1000 ton per year, and we converted into kilomole per hour as our calculation was did in kilomole per hour, and it was 3.56735159 kilomole per hour. And our production is in two streams, which is one output is a product ethylene, which is 1.8816250099 kilomole per hour from the separated column, consists of methanol, dimethyl ether, water and ethylene. And next is from the quench, where the ethylene production is flow rate is 1.64809704 kilomole per hour, consists of dimethyl ether and ethylene only. So now I'm entering for my first two units, which is a first unit is a cracking reactor, and the temperature for cracking reactor is 450 degrees Celsius, and pressure is 1497.2 mmHg. The flow rate of input is 3.56735159 kilomole per hour, and the output flow rate is 3.56735159 kilomole per hour. So the input stream and output stream temperature pressures are the same, which is 450 Celsius, and pressure is 1497.2. The function of this cracking reactor is to heat up methanol to form a single chain hydrocarbons and release of water. As you can see here, the equation used is 2CH3OH equals to H2O plus DME, where 2 mole of 2 mole of methanol will produce 1 mole of H2O and 1 mole of DME, and the fractional conversion for this process is 98.29%. Next, after that is entering to a splitter, where the temperature for the splitter is 450.05 Celsius, and the pressure is 1497.2 mmHg. And from the splitter it splits into two streams, which are the top stream consists of vapor and the bottom stream consists of splitter. Its function is actually, the splitter function is actually to separate gas phase and the liquid phase. So as you can see, the top is a gas phase, where the flow rate is 1.70424848 kilomole per hour, and the temperature is 12.545549653 Celsius, and the pressure is 1497.1254 mmHg. And for the bottom stream is actually the flow rate is 1.8207511313 kilomole per hour, and the temperature is 100.251486 Celsius. The pressure is 14971254 mmHg. It is calculated for both streams by using TBP for our gas phase and TDP for our liquid phase, and we use N-times equation and Rolle's law to determine the composition itself. For this cracking reactor, we use the equation and the fractional conversion to find the composition. So next we are entering for the condenser, which is the temperature for condenser is negative 30 degrees Celsius, with the pressure is 1497.2 mmHg, and the function is to cool down the temperature of the input stream to a desired temperature in the output stream. So this actually condenses a gas phase into a liquid phase. From a splitter, the gas stream enters at a flow rate of 1.1 1.70424845 km per hour, which the temperature is 12.5459635 Celsius, and the pressure is 1497.1254 mmHg, and goes out at a temperature of negative 30 degrees Celsius. The pressure is 1497.1254 mmHg with a flow rate 1.7042 km per hour, which actually same input equals the output because it's a non-reactive process. So next you will enter to the mixer.
Next is the mixer. The mixer's temperature is 70 degrees Celsius with the pressure of 1497.2 mmHg. So there will be two streams entering the mixer. The first stream will be from the condenser with the mass flow rate of 78.20958 0.79 kg per hour, and the downstream will be from the splitter with the mass flow rate of 34.6008743 kg per hour. So the purpose of the mixer is to mix two streams, which is from the condenser, which the condensed liquid from the upper stream and the liquid form from the lower stream, and then the streams will be mixed and exit out in one output stream with the mass flow rate of 112.8104551 kg per hour with a Celsius of 70 degrees Celsius and pressure of 1497.1254 mmHg to the conversion reactor. Next will be the conversion reactor.
Okay, moving on to the next unit. From the previous mixer, the molar flow rate is 3.529 kmol per hour, and the temperature is 70 Celsius. In the conversion reactor, the function is basically to generate ethylene and water as byproducts. So the equation for the reaction is CH3OCH3 to C2H4 plus H2O. The fractional conversion of the Me is 95%. So the outlet molar flow rate is 3.529 kmol per hour, and the temperature is 450.05 degrees Celsius, and the pressure is 1497.125 mmHg. Moving on to the next is the splitter. The function of the splitter is basically to separate gas phase and liquid phase. The inlet molar flow rate is 3.529 kmol per hour, and the temperature is 450.05 degrees Celsius. The pressure is 1497.12554 mmHg. And basically, the upper streams is the is in vapor state, and the lower stream is in liquid states. The molar flow rate of the upper streams is 1.649 kmol per hour, and the molar flow rate of the lower streams is 1.8803 kmol per hour. So the method to calculate these units is by using the Antoine constant, Rod's law, and the Antoine's equations by using TDP and TBP. So moving on to the next unit is the quench. The function of the quench is to cool down the temperature of the input streams to a desired temperature in the output streams. So the molar flow rate of the inlet streams is 1.65 kmol per hour, and the temperature is negative 74.5064 degrees Celsius. The pressure is 1497.1254 mmHg. And the outlet streams is 14649 kmol per hour, and the temperature is 123.5 degrees Celsius. The pressure is 1497.125 mmHg. So
Okay, for my part, is the first unit is a mixer. The function of the mixer is simply to mix two streams, liquid and gaseous. And the two streams are mixed. One is coming from the quench at rate 1.6 kmol per hour, and one is coming from the separator or splitter at 1.88 kmol per hour. And the temperature for the unit is minus 70 degrees Celsius, and the pressure almost 1 atm. And the stream going out is 3.5 kmol per hour, is going to the separator. And the method used to calculate is just simple material balance. What's coming in is coming out. And the next unit is the separator, and the separator the streams coming from the mixer at 3.5 km per hour, and the temperature of the separator is minus 68 degrees Celsius and pressure at 1 atm, and splitting the gas and liquid phases at the gas phase going to 1.6 km per hour and the liquid phase going to 1.88 km per hour. And the function of the separator is to separate the gas-liquid phases into two phases. The quench. The quench is basically the function to cool down the temperature of the inlet stream. The inlet stream is coming from the separator, which is the upper stream in the separator, at 1.6 km per hour. The temperature of the quench is minus 116 degrees Celsius and pressure 1 atm. And the stream coming out from the quench is the same as the flow rate coming in, which is 1.6 km per hour, and temperature is minus 116 degrees Celsius at pressure 1 atm. And this is going out to the storage. For the costing part, we are usually calculate the amount of methanol we are buying at USD. We are converting with a converter 4.119 for each USD to RM. For the price of methanol, the lowest price is actually 1.7 ringgit per kg, and the highest price is 2 ringgit per kg. So the total mass flow rate for methanol is, as the lowest price is over 200 ringgit per hour, and the highest price is 250 something ringgit per hour. So as a normal costing price of methanol we are buying is over 1 million ringgit per year as the lowest price, and the highest price is over 2 million ringgit per year. For the ethylene, we are producing and selling use the same converter of 1 USD to 4.19 ringgit. So we are pricing of ethylene as the lowest price 5 ringgit per kg, and the highest price is 6 ringgit per kg. So total mass flow rate of ethylene per hour is as the lowest price over 200 ringgit per hour, and the highest price is 300 something ringgit per hour. So the cost price of ethylene would be as the lowest price 2,200 something ringgit per year, and the highest price is 2,600 ringgit per year. For the profits,
now I'd like to say about the profit analysis. To obtain a minimum profit, we'll sell the ethylene at the minimum rate. At the maximum rate, we will sell it at the minimum rate, which is 2,272,855.5 per year, while we'll buy methanol at the maximum rate, which is 2,050,012.80 ringgit Malaysia per year. So the profit of the company will be at the minimum, which is 206,455.5 RM Malaysia per year. To obtain the maximum profit, we sell ethylene at the highest rate, which is 2684475 per ringgit Malaysia per year, and then buy methanol at the lowest rate, which is 176,062,999.92 ringgit Malaysia per year. So the profit of the company will be at the maximum rate, which is 905,075 ringgit Malaysia per year. Now it will be a cash flow.
for the cash flow, this is our cash flow for 10 years from starting the work of our company 2023 until 2032, and seems to produce over 1,100,000 something ringgit per year. And this is the graph showing that our profits is going to be increased from 2023 to 2032, and seems promising profits.
Now we're going to say about the conclusion and the recommendation. The conclusion and the recommendation, the first thing will be capacity and the production planning should be taken into consideration during the negotiation with the potential customer, and we can use catalysts such as SAPO34 to increase the yield of ethylene, and it is more facial and efficient and cost effective than the conventional ion exchange process. Investigate further the operating conditions and the performance of the reactor plant. This may incur a large compressor duty needed to perform this separation process, which would increase the process separative capital and also operating costs. High conversion of the methanol and dimethyl ether will increase the yield of ethylene. Material flow around each of these pieces of the process equipment were balanced as the total amount of the input was equal to the output, all the processor equipment of the design were having negligible heat duties except for the condenser. That's it from Oletex Sdn Bhd. Thank you.